is Dan and I are going to tag team. We're old hands at this. And we're going to be giving a foundation in programming language theory. And so the thing I want to say is that, like everything at the summer school, it moves fast. And so I will, what I want to mention about our lectures in particular is we're going to be covering a whole bunch of material pretty fast, and every single bit of it you'll see again with another of the lecturers in a more specialized and even faster and more intense form. So we're kind of giving you an on-ramp. That's the whole idea. So we kind of organized our lectures so that they pretty much match up with what comes later. So that's the plan there. The other thing I should mention is that I hope you understand what I'm saying, and you should ask questions and so on, and feel free to do that. But you should also expect to a certain extent that if you don't have experience, it takes time to learn stuff. So let it wash over you and try to do the homework assignments, and over time you'll get the idea. In other words, don't feel bad if you're not like mastering everything in the first moment, because we're going to be throwing a lot of ideas at you, and some of it gets a little technical, so we'll show you. On the other hand, in exchange, you're at the Oregon Summer School, so this is the place to learn about programming language theory, and you'll get the straight scoop here, and it will benefit you a lot, I think, if you're interested in doing research or other work in programming languages area. So that's the kind of trade-off. Okay, so that's the plan. So I'm lecturing now, and then Dan later this morning, and then we're alternating, and I guess we have a total of 6 lectures planned, eight lectures planned, and there's a lot of material we're covering. I'm mainly working out of my book, Practical Foundations for Programming Languages, which is available on the web. There's a web page. If you get twiddlerwh/pfpl, there's a whole web page there. In particular, there's a commentary and errata, and there's a preview edition you can have a look at if you like, and that's there. And pretty much everything we're doing, as was mentioned on the Piazza yesterday, I think we put it up. We listed the chapters we're working out of. Of course, you should put the book under your pillow and understand everything that's in there, but we're going to make a selection of things to take a quick tour through it. Later this afternoon is a work session. There's a certain number of things I'm going to gloss over in the beginning, and if necessary, I can lecture on them separately or talk about them separately. In particular, I'm not going to dwell on issues of what are binding in scope. So I will mention that and substitution and things like that. It would take me a whole lecture. So I'm going to take that as a given because you can pick it up. But I will say that almost nobody who thinks they're an expert in programming languages knows a damn thing about binding and scope, and every language that comes out has some, complete botch of a mess of it. And so it is important that you learn it. I'm not dismissing it as if it were unimportant. It's just a practical matter for sort of getting going. Okay, so that's a few preliminaries, and I can help, and Dan and whoever can help. Oh, and the other thing I wanted to say is, please feel free, and in fact, I would encourage you all to help yourselves. Everybody, some of you know a lot. Some of you maybe don't know as much, and some combination of things, you should all be able to find ways to help each other learn all the material. That makes it the most fun, and that's a good way to for everyone to get up to speed. So don't, collaborate at will. We're not giving you a grade or anything at the end, and I hope that will be another tool for you to get up to speed with what we're doing. So unlike previous years, we actually have written material for you, so you can look in the book. So that'll be helpful. Okay, so let's get started on the technicalities. So the thing I want to do is we're going to start out. I've got a little war injury. I got into a fight with somebody over object-oriented programming, and now my foot hurts. So I'm limping around. So don't mind that. So what we're doing is we're starting out, and I want to start out with something which is a fundamental bifurcation. And you'll see it comes up in the theory between partial and total programming languages, PLs. That is, whether you can have divergence or not, whether functions are partial or whether divergence is possible. Lots and lots and lots of people gloss over this, and all sorts of confusions arise from not being careful about it. So what we're going to do is in the first 4 lectures, 4 I think it is, if I remember right, certainly the first 4 lectures, we'll be concentrating on the total case, okay, where lots of things are simplified. Things are simplified in a certain way, so they're simpler. And in a certain manner of speaking, they're more mathematical, okay? You'll see why as we go along, and that's what we're going to do. And then we're going to talk about, the other lectures, we're going to talk about partiality, okay? And it's also quite mathematical and elegant and so on, but it's a lot more complicated in certain respects. Now, one of the mistakes that people make in talking about programming languages is to have a partial programming language and pretend it's total and like tell you that all sorts of algebraic laws hold and stuff that don't hold at all, okay? So we have to be careful about this, so I want to really draw this distinction straight away. So we'll be starting out with some total functional programming, okay? So the first thing I'm going to talk about is the E. coli of total programming languages, which is a language derived from a system introduced by Gödel called Gödel's T, okay? This will be starting out. And the idea is that it codifies higher order, meaning we have higher order functions, principles of higher order functions, and an inductive type, plus an inductive type. And in fact, it's for various historical reasons, it's the inductive type, the natural numbers. But I want to illustrate it as an example of an inductive type. And if I have time, I will throw in also a coinductive type for the reasons of expressiveness to show you how these things work. So we'll see how it goes. But we'll start out with Gödel's T. Okay, so that's the idea. So what we do is whenever we're defining a programming language, we give a definition in terms of its statics and its dynamics, okay? So that's the general flavor of how we do it. So the statics is telling us what are the programs, and the dynamics is telling us how do they run, what do they mean. So when I say what do they mean, I mean how do they run, okay? I mean, after all, we're talking about code here. We're talking about programs, and highfalutin notions of meaning are parasitic on the fundamental notion of how do you run the damn things, okay? So it's important. So this is my baseline of what we talk about. Meaning is, first of all, we talk about how to run them. Okay, so that's, I think, is quite important. So the way we do this is I use a formalism. So the idea that we use is I'm only ever concerned with abstract syntax. I will make up concrete syntax on the fly according to my whim, okay? I don't give a damn about that, okay? So the abstract syntax is defined. We use what are called abstract binding trees, and I'll just show them by example, okay? And these are basically, you might have heard of ASTs, but they have binding and scope, okay? Which is what we have here, and that's the thing I'm going to gloss over. So the first part of the book, chapter 1, is concerned with abstract binding trees, and you can read up on that. So I'll assume you know about this. And then I use a notation that looks like context-free grammars, but it isn't. I'm really specifying a signature of abstract binding trees. So what I'll do is I'll say my expressions, well, I have two things that I care about in the language. One is I have a class of types, which I'll write tau, and those have natural numbers and total functions. So the idea is that, okay, so we'll get to that. And then we have expressions. And the expressions, I'll just rattle them off, and then when I write down more of the statics, okay, then I will tell you what they all mean. So I'll just rattle them off. So the meaning is here, this is really concrete syntax for a binary operator arrow that takes two arguments, which are types. That's the way you're supposed to think about that. Okay, I always have variables. I'm going to define my natural numbers in unary, so I have 0 and successor. The reason to do that is I want to emphasize the inductive structure. We're trying to get at like the core principles of what's going on. Okay, so that's what I want to do here. There's going to be an operation called iter. I think I've forgotten what I called it in the book, so don't mind me if I do these differently. Then the syntax is a little different than in the book. Okay, written like that. And I'll come back later to what all that stuff means. Of course, we have lambda. This is Oregon Summer School, after all. So of course we have lambda abstraction. And if I didn't miss anything out, that's it. Did I miss anything out? No, I think I'm good. Okay. So that's my notion of the syntax. So what I'm doing is I'm using various forms of parentheses and stuff. I group things according to what suits my whim, okay? If you look in the book, you'll see the official, like what the syntax is. So don't get too hung up about the exact notation, okay? But understand what it means. So this, for example, has 3 arguments, okay? There's an expression, another expression, and this is an expression that has a bound variable x in it. It's a binder in this position, okay? In the same way that x is bound within E here, this would really, if you want to write this out, looking more like it does in the book, it would be written like that. Lambda is an operator that takes a type as an argument and then an expression with a bound variable in it, which I'll always write like that, okay? So that's the kind of thing we'll be doing. So that's just the raw syntax. And then to define the dynamics, I'm going to define 2 things. I'm going to define, because our execution model for these kinds of programming languages that we're studying at the outset, a little later it'll get jazzier, but right now, is we have the notion of when is an expression a value and the notion of transition. So this is a transition, which is one step of evaluation, one step of simplification or evaluation, if you would like to say that. Okay, so that's the setup. So we're going to define these things. And the overall strategy uses one of the most important ideas in computer science, which is, I'll even mention him by name, is Gordon Plotkin's what is called structural operational semantics. If you're not familiar with this structural operational semantics, and maybe for the next couple of days you'll like to use its acronym, which is SOS, okay? And so you can think of it that way. So structural operational semantics, you missed the joke. Never mind. So that's the idea. So Plotkin, this is a way of defining the meaning of programs. Now, what's absolutely preposterous in 2016 is that people produce programming languages and they supposedly tell you what they mean by writing some sort of reference manual, maybe, kind of, sort of. It's ridiculous. It's completely ridiculous. We have the tools so that we can give precise definitions to what the programs are and how we run them. There's no excuse to be not doing this, okay? The old Unix idea from the 1970s of trying to use some legalistic sounding language in an English document was fine for the 1970s, but it isn't fine anymore. But that's what, lots of things are done that way, so you might as well think that's just the way it is. But I'm trying to show you, like, we have really good tools for specifying these things. Okay, so now let me specify further the statics. So the statics is specified by typing judgments. So I'll have the notion of typing, which I will write like this. I'm sure many of you are familiar. And where this guy is what is called a context. And what it does is it tells you what the types of the free variables are. Okay, so it's a bunch of variables together with their types. We usually write a colon saying that x1 is assumed to be of type tau1 and so on. So this is our notion of typing. I'll mention in a moment that this is another thing that we should be careful about. This is not just like, oh, whenever you want to do whatever you want to do, you write it down with these funny looking symbols and you're good. No, okay? No. This is going to present something called a logical consequence relation. Okay, and I will explain what that is a little bit in a moment, okay, before I get to it. But it's important that it be a logical consequence relation. The reason is that, I'll come back to why, but the main idea is that you're supposed to think of this as some kind of an entailment. The idea that assuming this is the case, then this will be the case, and that has to be well behaved in a certain manner, which I'll explain in a minute. Okay, so this is usually inductively defined, so this is all part of the fast on-ramp here. So it's inductively defined by a bunch of rules. Okay. Now, the rules, you should understand what the rules are doing so that you get like the inner game here. Okay, so the important thing about inductive definition of a bunch of rules is we think of this as a three-place relation. And what we do is we say it's the least relation closed under these rules. The least relation or judgment, whatever we'd like to say, closed under the following rules. So the rules are a way of presenting a closure condition, of saying that if something is in there, well, as we'll see in a minute, then something else is in there. You don't get to write English on the top of the rules, okay? So there's a whole cult of like fake inference rule stuff going on where people write papers with all sorts of rubbish, and they write down typing judgments that don't satisfy the criteria of being a consequence relation and don't even qualify as a set of rules. So I want you to be careful so you understand what really is going on, okay? That's the thing. So imitate the content, don't imitate the form, okay? That's what's important. Okay, so typically, so for growth T, I'll give you an example. So what we'll say, okay, so for convenience, I don't have to do this, but for convenience, I will see that these are all unordered. Because in a language as simple as Gödel's T, the order doesn't matter. There are other languages where I have to be careful about the order, but right now I'll be a little sloppy. So I'll mention that this is treated as unordered. There's no order to the variables. So that allows me to write something like this. It says, if you're assuming that x is of type tau, then guess what? It's of type tau. Okay, so that's the principle of reflexivity. If you're assuming tau, then tau holds because you assumed it. Okay, so that's first rule. But notice it's an axiom. So thought of as a closure condition, it means that whatever you're defining, this is a fact. Okay, because it's not contingent on anything at all. And the same will hold here when I talk about, I will say 0, I just write z often, is a natural number. That's contingent on nothing, okay? That automatically is the case because I'm specifying it by a rule. So this would, a lot of times, so this would be the variable rule, otherwise known as the hypothesis rule, otherwise known as reflexivity, although that might seem a little weird to call it reflexivity, but I'll explain why in a moment. Okay, this would be called, I'm not sure how many of you are familiar, we might call this Nat introduction Z. So we use the terminology of Gensen here. Gerhard Gensen, and worked in the 30s as a German logician who laid the foundations for logic properly, and then for the next, 7 decades, people pretty much ignored it, and then they finally realized, oh, you know what, Gensen had all this right in the first place. So now he gets the right credit. So he used the terminology of introduction and elimination. So that the way in which we define a connective or a type like nat is we tell you how to introduce natural numbers, like what are they, like 0, and I'm going to write successor here in a second. And then there's what's called natural number elimination, which is how do you compute with one of those things. And there's a beautiful pattern of intro and elim, and that was due to Gensen. So it's kind of cool, like that he really nailed this. I mean, it's been elaborated upon to great extent, but basically he got it all right. Everything he said, he got all right, and it's definitive, and you can't do better. It's really astonishing, and back in the 1930s. Okay, so sometimes I like to throw these things in because I have appreciation for those kinds of things. So if you don't, well, all right, just indulge me. Okay, now here's our first conditional rule that says, if you already know, so to speak, that E is a natural number, then the successor of it is a natural number. And this would be called maybe nat introduction successor. I might write it like that. Just, you need some way of naming these things. So that's what we're doing. So these two together constitute the introductory rules for the natural numbers. And the question is, what's the eliminatory rule? Let me come back to that because it requires a little bit of explanation. It'll actually be easier if I talk about functions first, and then I'll come back. So I'm going to write here, I need space. So if you're taking notes, although you don't have to, everything's written down. So don't feel you have to transcribe everything because everything's written down. Okay, so I'll write nat elim, but you'll need some room here. So I'll come back to that in a minute. Okay, so let me look at what happens with arrow introduction. Okay, so the idea is if I write lambda x tau e, I'm going to claim, let's call that tau 1. I'm going to claim that this is a function from tau 1 to tau 2. It stands for that. So if you've never seen lambda notation before, you've seen it in math when people do that. They say, give me x in tau 1. In fact, often a lot of math that you would study, it's all already assumed it's like the reals or the complex numbers, whatever you're talking about, and then you don't bother to write that. And then you say x is sent to e, whatever this expression is, that involves x. I'll write a little x here to indicate, okay? Well, that's what the lambda is. It says, give me your argument x, and then e tells you what the result is as a function of x. Oh, what does it mean to be as a function of x? Oh, it means that the body has to be well typed, that's a 1, has to be of type tau 2, the range or codomain type. given that the variable x is assumed to be of type tau1. Okay, that's the whole idea. So the notion of a function is parasitic on the notion of a mapping. And in fact, Ed this afternoon will be using terms like mapping, or he'll use a term like morphism, and maybe some other words, but those are probably the likely ones. Okay, and Ed will be talking about that this afternoon. So in Ed's notation, just to foreshadow, he would say something approximately like gamma cross tau1 arrow, long arrow, because it's not this, is tau2. That's the way he would write it. And then below the line, he would write something approximately like a lambda of e, whatever that turns out to be, this long arrow, and then you use the notation tau2 to the tau1, exponential notation. And that means this input and that output. So that's the same thing. Okay? So I'll just throw that in just so that you can see there's a coherence to our plan. We have a reason for teaching everything we're teaching, and they all fit together, I hope, in a pretty reasonable way. And we'll know at the end whether we succeeded. But that's the idea. Okay, so that's the arrow introduction. And the arrow elimination, so let's look at elimination here. So that way I can scale you up to what's going to happen in a minute. So the elimination rule says this. What do I do if I happen to have around something, some expression whose type is tau1 arrow tau2? What can I do with that? So you notice this has the flavor of create one of these guys out of some other stuff. Now I say, well, now that you've created one, okay, what do you do with that guy? Well, you could guess because you're familiar enough with these things. It's a function, so what can I do with it? I can apply it, right? That's all I can do. And I have to apply it to an argument of the correct type, so this would be tau1 in this case. And then we use notation like, I don't know, officially I think I write app E1, E2 in the book, but we always write E1 applied to E2, and that's type tau2. So you'll notice this has the flavor of introducing the arrow, and this has the flavor of eliminating the arrow, okay? Elimination, maybe you don't like that word because I'm not like causing it to cease to exist or something like that, but it's just like that's Genson's terminology. So basically, what do I do when I have one? Well, I apply it to an argument, and now, so to say, I've gotten rid of it. Well, I haven't really gotten rid of it. That expression might still be around, and I can still use it, but anyway, in a certain way, I've gotten rid of the arrow by applying it, okay? And so here I've introduced the arrow, so that's the idea. Okay, so that's the setup for that. So now the horrible looking rule for iter, that's why I left it for last, okay? So the idea is that we're going to work like this. We're going to say, suppose I have a natural number. Here I showed you how to introduce two natural numbers. Suppose I have a natural number, what do I do with the damn thing? Okay, that's the thing. What can I do with it? Well, the important thing is that the natural numbers here are an example of an inductive type. I'm going to sneeze. One of the pleasures of Eugene is if you have grass pollen allergies, you'll be suffering for the whole time you're here. Okay, so what do we do? So the idea is I want to eliminate this natural number, so to speak. So in Ed's terminology, he'll say that nat has a mapping out property. And in fact, okay, and we're going to explain what the mapping out property is, meaning mapping out, that's a synonym for elimination. Okay? That's the idea. So Ed will explain these kinds of things in those terms. Okay, so the idea is I've got a natural number, I want to map out of it, I want to do something with that natural number. Well, it's an inductively defined type, and this rule is going to be the thing that expresses the fact that it's an inductively defined type. So there's one of the things that's hard to get used to with category theory is the way in which things are defined and concepts are manifested exactly by telling you that certain mappings or morphisms or things exist. Okay, certain pieces of programming syntax exist. You have to get used to that a little bit because you probably learned all this kind of mucking about in sets and stuff. You're going to forget all of that. That's totally useless, okay? That's of no value at all. So Ed is going to talk about that in more detail, but I'm trying to make the connections. So the idea is that what do you do with a natural number? Well, you proceed by induction, which in programming terms means you count up to that number, okay? So what does it mean? What else could you do with a natural number? The whole point of a natural number, in fact, in elementary school, you might have learned them as counting numbers. Sometimes they use words like that. And then they start with 1, which is terrible. So you start with 0 like a civilized person. Okay. So we count, okay, and we start with 0. Okay. So the idea is I want to compute a function or write a program that's a for loop. Okay. But it's a for loop, but it's not a for loop with imperative stateful computation. It's a for loop with computing with functions. It's a limited kind of recursion, you could say. So what do? If I want to know, so the idea is that from that natural number, so I'm going to write in some stuff here, E will come here and the result will be of some type tau. Because the point about an induction principle is that it's a mapping out. Where it goes, nobody knows. You can go anywhere you like. So the type tau will be whatever you want. What matters is that you're mapping out of this. So what I do is I tell you what is the answer when E is 0. And then I tell you, as a function of the answer implicitly when when you have some number E, or let's call it N to make it not confused with that letter. So if you have some number N, or X, I wrote it here, so some number X, I tell you how to go one more step, okay? So I tell you how to get into the game, and I tell you how to iterate. Take the answer from the previous recursive call and give me the answer now, and then I have something called iter, which might be all decorated and stuff in various ways, and we'll write x.e1, and then not to leave any space here, I'll just use the parens like that, and that will be of type tau. And then we're done. Okay, that's it. Ed will explain this in terms of a concept called a natural numbers object, an NNO, and it's the same thing, exactly the same thing. Okay, there's no difference at all. This is what Gödel's T is all about. Okay, so that's the statics. So we're done with that. Oh, it presents a consequence relation. So the notion of a consequence. Okay, I'll write it out for typing. Okay, the principles are these. It is a fact that this is the case. Well, that's by definition. Okay, but that is true. Okay, but these are the things I demand. The very important thing I demand is this. If I have E tau, and I assume X is of tau, and I get E prime is of tau prime, then it had better be the case. So in fact, let me not write it like this, because then I have to use the terminology of admissible rules, and let's not do that. So let's say, if this and that, okay, then guess what? You can plug in E for X and E prime, and you get tau prime. This is what I like to call, I'm fond of calling this the LD rule. Okay? The Unix utility LD, that's what it's implementing. Okay? That's what linkage editing is. Right? You assume you have a library named X, like standard, the Unix standard library or something, and you program with respect to it, and then you link in the actual code, and you get your program, which is linked. LD is nothing but a implementation of substitution for the most perverse syntax in the entire world, like cough files and shit like that, okay? It's the perverted syntax, but that's what you do, okay? So this is substitution. So if you want to say it, so it's substitution. And Gensen called it cut. And so or Schnitt, and we're all used to calling it cut. So sometimes we'll say, oh, we'll cut in E here. That's the terminology. That will happen, okay? So that's very important. These are undeniable. This tells you that variables behave like variables, okay? Because as you learned in elementary school, variables are given meaning by substitution. You plug in for them, okay? Those things are variables, okay? The things that almost every programming language calls variables are not variables, okay? And we'll get back to that a little bit later, okay? I want to insist on the distinction because it's important, okay? So 3, we'll get to that. So 3 is, this one seems almost like you don't have to say it, which is any extra hypotheses, let's write primes there, don't count. And this is called weakening. If I can type check something using these variables, well, hell, you can think of it as type checking using these variables, except that you don't use that one. Okay, it's like a degeneracy. It's like something you don't care about. Okay, so that's called weakening. These might seem self-evident, but what I will mention here is 3, 4, and 5 are absolutely critical. So what I will say here is simply repetitions don't matter because it's too tedious to write everything out. Repetitions of hypotheses don't matter. Okay, and the order of hypotheses doesn't matter. But I built that in because I said, oh, let's just consider it a bunch of variables given a type, and then, but officially I could assume X twice being the same type, and it's a little bit trickier than that, so I don't want to get into all the technical details. But the idea is that if you have, well, here's the idea, let me write it out. So if I can get something with two variables of the same type, if that, let's call that tau 1 and tau 2, and I can get this, then I can actually also type check, oh, no, I'm sorry, that should say tau, and this will put tau prime. Okay, then I can also put x tau, and then I can just essentially do substitution. I can plug in both x for both x1 and x2. So I'll write xx for x1, x2 in E prime, and that will be tau prime. So that's what I mean by repetitions don't matter. If you can type check this, you can type check that. The force of it is that I can plug in the same variable for two different variables. Now, in your school experience, one doesn't even talk about this. It's self-evident. But in fact, all of these are deniable, meaning that one can talk about meaningful type systems without those. These are undeniable. You cannot get anywhere. So in Ed's terminology, 1 and 2 are essentially the definition of a category. I'm just giving you a taste, okay? That's essentially the definition of a category. These are properties of particular categories, okay? That's what will happen, okay? So he'll tell you more about that, okay? So that's the idea. So you don't get to like write any old random thing with horizontal lines and turnstiles and Greek letters and call it a type system, although many people do. So I've seen lots of things like that. So that's the idea. Okay, let's look at the dynamics so we can move along here. How do we specify the dynamics? So the idea is that we execute closed code. Okay, that is no free variables. This again is common sense. I'm not going to talk about, technical details like dynamically linked libraries. That's just a hack for various purposes. But in the end of the day, whenever you're running a program, you've got all the code there. That's just common sense. All the code is right there. There's no mysteries. You can't run something that uses a library without the library. You have to have the library there. Okay, so we're going to run closed code. So that's the idea. All right, and so we're going to define the judgments I mentioned before about being a value and about transition. We're going to define in the following way. Here are my values. I'm going to do this in a somewhat arbitrary way. I have a method to my madness, and I'll mention something a little bit later about this. So 0 constitutes a value. I'm going to just say any successor is a value. Okay? It makes things extremely simple. And lambdas are values. Now, what are alternatives? Well, on these things on the board, an alternative is I might have demanded that E be a value. Okay? I can do it either way because I'm in a total language. Now, one of the mistakes people make is if you fail to distinguish between partiality and totality, you carry over ideas that are meaningful in a total setting into the partial setting, and then you make a mess. Okay, so messes have been made in this dimension. But right now, by dealing only with totality, this is completely just like optional. Later, we'll talk about cost semantics and evaluating complexity. That will come up, but right now we're not going to be concerned about that. We're just looking at the very basics. So I get to have a choice here. I can do it either way. If I were working in a partial language, I do not have a choice. And in fact, writing it like that is wrong because it isn't the natural numbers. So we'll get to that later. Okay, so those are my values in this language. That's the way I'm going to define them. So this isn't actually here. I'm just suggesting that one could do it. Okay. All right, so those are my values. And then I define how you evaluate things. And it's really pretty straightforward. So let's see, what do I have to do? I have to tell you how to evaluate. What could the source of running be? An elimination form. That's the way in which we get things to run. And when do the elimination forms run? When their principal argument, I didn't use that terminology a moment ago, each of the elimination forms has a principal argument, which I tended to write last. So this is its principal argument. This again comes to us from the 1930s. Okay, its principal argument, and that's here, is its principal argument. When its principal argument is a value, then the elimination form can execute. So I'll show you how that works. So let's do application. So if I have lambda, which is a value, and it's applied to an argument, so that means I have an application and its principal argument position here is a value because I just said so. Then this guy can actually run, and it runs exactly the way you think. You plug in E2 for X and to E, and that's your next step. Notice how it fits together with the structural properties. Because I have the principle of substitution, I haven't proved this for you, but we'd have to prove it. Whenever you write down a type system, you know, it's a little, the official story is a little bit involved. I really have to prove these things to show you that I defined a type system properly, okay? You can't really skip that. If you're good after a while, you get experience, you know. But one of the reasons people do mechanization is because that way you can deal with stuff like this pretty easily. Okay, so officially I had to prove this. I don't have the time to prove it to you. But the fact that this is the case is, look at the statics of lambda. What I'm really doing is the type safety theorem on the fly. The statics of lambda says if you have a lambda, it means you have an open term with a distinguished free variable. Because I have the principle of substitution, it means I can plug in an argument right here and get the substitution instance, and it will still have the same type. So we will talk about that in a minute. So this makes sense because this implies I have E with a free variable X, and by the substitution principle, I can actually do this substitution and everything will be honky-dory. I'll make that statement precise momentarily, but that's the idea. Okay? You with me? Interrupt or at any time if you like. I want to make sure you're with me. Okay. Now the one for the iter, or whatever I called it, okay, I had some tau here, and I have E0 and I have X dot E1. The important thing is, okay, what happens when the principal argument is a value? Well, one of the possibilities is it's Z. So guess what? I then transition, the way I evaluate that is to E0. E0 is the thing that tells you what to do when the argument is 0. So when the argument is 0, you do that. Okay? All right? Now, what if I have an iter, same one, and the argument is the other form of value, it's successor of E. I don't know anything about E, but I know it's a successor. So now what do I do? Okay, well, this is what you do on 0. A successor is not 0, so I have to figure out, I'm going to use this guy. So remember, if you look at the typing, remember I described it to you as, tell me your result on the predecessor, and then I will turn that into the result on the successor. So using the principle of substitution, what do I do? The transition is, I'll write it below the line here to give myself some room. I'm going to do a substitution for X, that's the X, okay, in E1. And what am I going to substitute? The result of doing the same damn thing, that's this part. So this hasn't changed. I could just throughout call this I, and then what I'm saying is I of Z transitions to E0, and I of successor of Z, of E, transitions to, that'll help it fall into your I, just calling that I, will be the iter, which will be I of E for X in E1. So that's what I'm going to do here. I'm going to write E. This is the predecessor. The successor, here's the predecessor. Here's its predecessor. But if you write it with I, it looks a little nicer. Okay, so you can write it like that. The point is, none of this is varying. It's a little heavy to push it around, but none of it is varying. Okay, so that's it. That's the dynamics of Gödel's T. Okay, with this, you can run programs. So exercise. Oh, I can't resist. Define E factorial using the recursor, or the iterator, I call it. Okay. You can write that down. Okay, that'll, it's probably in the book, but anyway, you can try to write that down. I don't want to spend time on that. Okay, so now I want to mention, okay, so that's it. That's the statics and dynamics. Now let's talk about safety. And then I want to talk about some very important extensions and an important theorem, which will lead into this afternoon's lecture. Something's wrong. What? Question somewhere? Oh, yeah.
Do you define congruence rules or whatever? So, like, if you do function application, don't you need to have a rule?
Oh, yes, you're right. I got carried away with my voice. Yep, so John asks exactly the right question. I forgot to say something. Okay, which is, these are the rules when you know that something is a value, but how did I ever get into that position in the first place? Ah, right, that's what I forgot. So let me write here. No matter how many boards you have, you never have enough. So, all right. Okay, good. So, yes, so I need some additional rules which say, well, suppose I have E1 and E2, all right, and that's not a value, it's not a lambda. What do I do with that? Do I just like die? No. Well, I evaluate E1. I say, well, simplify E1 in the hopes that you're going to eventually run into a lambda. So I do that, and then I transition to that. So that just says in place, simplify E1, and keep doing that until it gets to a lambda, in which case that rule over there fires. So I forgot about that. And the same thing applies to the iterator. Okay? So I have this iterator, and E is not yet of this form. Then what do? I say, well, just work on it until you run into zero successor. It gets a little heavy, I realize, okay? But this is why we have computers, so you don't really have to write all that down all the time. But anyway, this is the idea. So I need those two. I would have noticed this as soon as I did the next thing. So it's very quick here. Okay, type safety. I like to think of it with this picture in mind, so I'll show you. Preservation says the following. If I have a closed program of a certain type, and I'm able to simplify it, then what I simplified it to has the same type. The type is preserved across execution. So this is basically, unlike, sort of low-level C programming, I can't get a bus error by like branching into Nowheresville, okay? If I start with something that makes sense and I take a step, then I will continue to make sense. No bus errors, okay? So that's the idea there. Second thing is progress. And this is where my mistake would have shown up if I tried to do this proof, which is you say, if I have a closed term of this type, then either one of two things obtains. E is a value, we're done, or E takes a step. So there's no illegal instruction, okay? There's no way you can have a well-formed program and you don't know what to do next, okay? Either it's a value and you're happy and it's done, or you can take a step. No illegal instruction. See the point? Okay? So that's it. And these two things fit together because, you see, if I have a well-typed program, either it's done, or, and it has that type because that's it, what I'm saying, or it can take a step, which by preservation means it's well-formed, which means by the result of the preservation, it's the E prime now that is either a value or it can take a step to E double prime, which by preservation, since it took a step to E double prime will be well-formed, and so on. So you can see there's a pas de deux here. Okay? That's what happens here. So that's how that works. How do we prove these things? You prove it by induction on this, and you prove it by induction on this. In other words, to prove preservation, you go through all the possible transitions, knowing that the starting point is well-typed, and you argue that this is well-typed, using the structural properties I mentioned before, the consequence relation properties. How do you prove this? You go through all the well-typed programs and you show for each one it's either a value or it can take a step. And this is where my mistake would have, my oversight there would have shown up, because I would find myself unable to deal with an application whose function position is not a lambda had I not written those rules down. So in reality, the way this works is, this is the methodology. If you want to write down a programming language of statics and dynamics, it's incumbent on you to prove preservation and progress so that you know you've defined something meaningful, okay? If you can't push the theorem through, probably you left out some rule, you screwed something up, okay? And then you go back and do it again until you get the whole thing to fit together, okay? This is how you get stuff to fit together, okay? So that's the notion of type safety. I'm not going to go any further than that. We're going to concentrate on deeper semantic properties of the language. Okay, so now I want to start to really put on the afterburners. So, I have something relatively minor to say, and then I have something important, very important to say. Okay, any questions so far? Are you with me? Yes?
In practice, do people, when you're trying to create type theory and semantics for it, do you just come up with random ones and check, and if it doesn't work, and then you try another one?
Do I just what? Say again?
So you have your own type theory.
Yes.
Programming language with the statics and dynamics.
Yeah, there's a back and forth thing, I think is what you're asking. It's arbitrary, but it's not, okay? A few years ago, Peter Fried, who's a famous mathematician, gave a lecture at Penn called "What is Mathematics?" And what it's kind of absurd, but it's kind of true. His ultimate bottom line was, it's the science of the non-arbitrary. Okay, that's what he said. That's what he said, it's true. So the point is, it's arbitrary, but it's not. It has to make sense, okay? And I'm trying to tell you what it means to make sense. So I can't possibly tell you what ingenuity could come down the pike. There's no way, okay?
I'm not questioning
okay. All right.
Whether these are useful or not. I'm just saying, in practice,
Yeah.
When you make a new programming language,
Yes, you go back and forth.
Can you sort of tell whether they'll be satisfied from experience?
Yes.
Right or wrong?
Well, the only way you develop that is that you suffer and do these proofs in detail for homework, okay? Because then you know every single corner, and then you develop proper intuition, okay? Believe me, I can pull down volumes of conference proceedings and point to you some total rubbish so-called inference rules. You know, it's like embarrassing, okay? Because people imitate the form without understanding the content, okay? So, yeah, so I'm trying to teach you what the inside game is. So you learn all that, and then you're good, okay? But you do have to do every detail of that proof so you understand, oh, that's how that works. Then later on, it's like, oh yeah, this is self-evident, okay? You still make mistakes, but because things get complicated. When you get full-scale programming language, the hard parts are the interactions between the features, okay? That's what's difficult. That's where all the bugs and problems come in, okay? Things interact in subtle ways. We'll get to that later. Like partiality. Like I'm going along with this stuff, and now if I throw in a while loop, I've screwed everything. It's a mess, okay? Things change, and I'll show you. The lecture on PCF coming up is more or less that. Yes?
Why is the system called OPLSS?
What's
did
that?
you come up with this exactly, or did people extract it from deeper?
Could someone relay the question? My hearing isn't
Why
good.
is it called Gödel's T?
Oh, why is it called Gödel's T? Because Gödel introduced it, and he gave it the name T in his paper.
What I'm saying is, did he write this down explicitly, or did people extract it from his work?
No, this is exactly it. And for me to explain that, basically Gödel, amongst many of his achievements, was to understand the computational content of proofs. So he was trying to understand the computational meaning of proofs in arithmetic. So it was a study in logic, but it was an interpretation that made explicit the programming language involved. And it's remarkable, okay? This was in the 50s. Computers kind of existed, but not really. You know, there were 3 of them, you know. Von Neumann was famous for saying, I forget the exact number, but something like, oh, the world will only never need 6 computers, or a number like that, okay? So it was early days, the 1950s, okay, so, yeah.
Yeah, so, you have the statics, you have the dynamics, and you prove
Pres-
constant
yeah.
preservation, yeah. So where do the consequence relations fit into that?
Well, unfortunately I erased them, but you must prove those when you define your typing judgment by a bunch of rules. You must prove that those properties hold.
And
So you prove that they hold, and where do you use them?
You use them in the proof of preservation in progress.
Okay. So
Okay.
I have also seen presentations of proofs of these things that did not include proofs of the consequence relations. The impression that I got is that you were sort of using them to define how substitution works, right?
No, I was not using it to define this. I was just making an allusion to these properties, I think, if I remember the way I did it. But the idea is, first you define the typing rules, which are obscured at the moment, and then you prove all the structural properties, because you're defining a consequence relation. It's very important that you do that, okay? That it have the properties of reflexivity or variable rule, it has substitution, and probably weakening contraction and permutation, okay? Although so-called substructural type systems don't have that. And then you use those properties, particularly substitution, to prove preservation in progress. Okay. So that's the methodology, and that's how it all works. Okay. It's all derived from logic. The nice thing is it fits. Like, that's why we appeal to like Gensen, who, it's fair to say, didn't know anything about programs or writing code, but he got all the right ideas because he was interested in the idea of computation. You know, that is part of what he was doing. Gensen gave a computational understanding of the rules of logic, which at the time was completely revolutionary. There was nothing like that. Okay, so that's important. Yep. Someone will have to relay that, but. Could someone repeat?
Did you intentionally leave off the rule for evaluating the argument of a function application?
Yeah, I did, because it's somewhat arbitrary in the total language and it simplifies some of the technical development. Okay. As long as I'm total, it's arbitrary. Okay. If I'm partial, then it's a different game. Okay. All right. So now the next thing I would like to bring up and then ask a hard question. Okay. So what I don't have time to develop it now. What I'll do is I'll give you a pointer to where to look in this. So the exercises, or at least the reading, is one, add products to the language. You're going to need this. So we have one and cross. So tau 1 cross tau 2 and the so-called unit type, or the single element type. Okay, I'm not going to be able to explain further right now because I have other objectives. Okay, the important thing, for those of you who really don't have much experience in programming languages, and I'm welcome, I want to, that's fine, I'm happy for that. You should particularly, if you don't have experience, you should particularly concentrate on sums. The reason is, it's the locus classicus of language design botches in the whole world, okay? Because nobody in the world practically, except for a limited subcommunity of PL people, understands sums. And the fact of not understanding sums leads to all sorts of nonsense, like null pointers, like that don't exist. There's no such thing as a null pointer. It's ridiculous. Okay? It's because of not understanding what are sums. Even the whole idea of dynamic dispatch and objects and so on is because of not understanding sums. So you can have a look at it. Okay? So this is, I don't have time to go any further. And then the one that's really cool is add streams. And this is, I don't know the chapter numbers off the top of my head, but it's in the book, in the book on the chapter on inductive and coinductive types. Just the early part, the introduction to that chapter shows you how to do streams. Then those infinite streams of natural numbers. So the thing I want to just mention here very briefly is here we have a language which I claim is total, but now I'm going to prove it to you. That's the trick, okay? But let's say I proved it, okay? It might come as a surprise if you're a little naive, and we all are when we start out, that you could have infinite data structures, like the stream of all prime numbers, all of them, in a language which is completely total. Well, how is that possible? Because they come to exist only on demand. Okay? That's the idea. So the thing I want you to get at here is it's an example of a coinductive type. So it's a dual, in a certain sense, of inductive type. It's also an it's an example of a limit. Okay, it's an example of a limit in categorical terminology and in categories, and it's kind of dual because we had nat, and it's inductive, and it's an example of a colimit. So you'll get some terminology of that. That'll be in categories, okay? So we'll explain that. Okay, this will be reading and off to the side. I can't lecture on it now, okay? All right, so we can always amplify in various sessions and stuff, but anyway, for my lecture, I won't talk about that. Okay, so now I want to ask you the following question. I want to prove the following theorem. And this is actually, Gödel proved something stronger than I'm going to prove, but it doesn't really change anything. So let me just attribute it to Gödel, okay? Morally, it's correct to attribute this to Gödel, okay? So I claim the following theorem, okay? If E is of type tau, then there exists E prime, which is a value, such that E multiply transitions 0 or more steps to E prime. And in fact, just to throw it in your eye, let me use the letter V to remind you that it's a value. And this would be called termination. Okay, so that's the termination theorem. See, I claim to you that I'm doing a total programming language, right? That's what I said. Well, there's no possibility of having an infinite loop. Everything is defined. That's what I claim. The question is, how do you prove this fact? Okay, so now someone asked the question earlier. So here was Gödel's objective. Gödel did this very interesting thing. He said you could take the proofs, and if you know the Peano axioms for arithmetic, okay, for doing reasoning and logic with natural numbers. If you take those axioms, he first said you can interpret the proofs, and at least in the constructive version, let's not worry about all that business. So it doesn't matter for my purposes. You can look at all the proofs, and you can turn them into programs. And then you can prove that if those programs terminate always, then that's true if and only if arithmetic is consistent. Okay, that's the important thing. So what it means is the proof I'm going to give of this requires by Gödel's other theorem, okay, requires methods that go beyond the scope of arithmetic. Okay, why? Because you cannot prove the consistency of a theory within the theory itself. That's Gödel's theorem for an axiomatic theory. So if I'm going to prove to you the termination of this language, I am, via Gödel's other work in the paper I'm referring to, I'm proving the consistency of arithmetic. So I need methods that go beyond arithmetic. So for those of you who are specialists, that's just a remark. Otherwise, I'm just going to do a mathematical proof. There's nothing objectionable, weird, problematic about the proof. It's a proof. Okay, I'm going to do this proof, and but I just want to mention that that's what its status is. Now, there's a lot of mystification and bullshit out there about Gödel's theorem and stuff. So we'll take any questions about the nature of proof offline. Okay, so this is the idea. So I'm going to give a proof. Okay, and what I want to do is I'm going to now invent the proof with you. Okay, so I need you to pay close attention. We're going to do this proof together. Okay, so suppose and to do it, as I'm going to use a technique called, now Gödel didn't have this terminology, it's called logical relations. This is a core, this is one of the most important ideas in computer science. Okay, it's extremely central, important idea. All of the subsequent lectures are going to use logical relations. Patty Johan will be using logical relations, probably Noam, everyone is going to be using logical relations in one form or another. It's the central idea. Okay, so you have to learn this. So I'm going to give you, so Gödel didn't use that terminology. Rick Statman gave it that name. I guess it might be because of Gödel's connection with logic. Okay, so I'm not sure, but they're always called logical relations now. So the theory of parametricity, the theory of polymorphism, is based on logical relations. So all the work on compiler correctness that's going on these days and compiler verification, logical relations. There's no other way. Okay? All right, so it's important you understand this. All right, so let's say we're trying to prove the termination theorem. You could say, oh, it's self-evident. You could say, oh, well, how could I possibly write something divergent? because I give you a means of counting up to a certain number, by a certain number, and I give you a way of doing function application. But I do higher order functions. Okay? In other words, I can pass functions to other functions. And things get pretty complicated when you do that because it's hard to understand what code is being run at any given time. Very difficult to get this. It's not, my first point is, it's not obvious. And when you see the proof, you'll see it's not obvious at all. Okay. So you can't just tell me, okay, it's obvious, that's it, we're done. Okay? It is by intent. I wrote everything in such a way that this would be true, but this is the idea. Okay, so how do we do this? Well, look at the form of the theorem. It's a mapping out property from the fact that E is of type tau. It's if this, then that. There's no other data. There's nothing else coming in. So you don't have any choice whatsoever on this proof, but to go through the typing rules one by one, okay, to figure them out. All right? So we can get started. So, okay, 1. It can't be a variable. E means can't be a variable. Well, because I'm looking at closed terms. So it can't be a variable, so that rule, oh good, we got that done. Okay. 2. Oh, 0 evaluates to itself in 0 steps, and it's a value. Oh, we're good. Well, maybe it's not so hard after all. Okay, so we do successor. What about the successor? Well, successor evaluates also to itself in 0 steps, and that's a value. This is partly where I've made life for myself convenient. Okay, so all right, so that's a value. So we're done. All right, so that's 0 in successor. What about lambda? We do lambda x tau e. Oh, well, that evaluates to itself in 0 steps, and it's a value. So we're done here. Well, that's 3/5 of the rules. Okay, so we're doing pretty well. All right, we get 60%. We're in good shape. Okay, now we say, all right, so what about E1 applied to E2? That's what my E is. That's E1 applied to E2. So what do we know by induction? By induction, E1 terminates V1 for some V1, and E2 terminates V2 for some V2. We just know that. I'm not going to, turns out, well, we'll see what we do, but we do know that. Why do we know that? Because the premise of the typing rule for this guy, E1, E2 applied to tau, tells me that E1 is of type tau2 arrow tau, and so it, by induction, terminates, and the argument is of type tau2, and so it, by induction, terminates. So we have that. And we know something even more, right? Because we know by the progress in preservation, okay, and by basically like this, and inspection, I'll say. What do we know about V1? Well, V1 is of type tau2 arrow tau. That's what I'm assuming. And V1 is a value. So what do we know? We can easily check V1 must actually be of this form. Let's call it E prime. Okay, we know that, right? Because if I have a value, a closed value of function type, look at the rules. What are the values? 0, that doesn't have function type. Successor, that doesn't have function type. Lambdas have function type. Okay, so we know that. And we also know that with x being in tau 2, E prime is tau. Why? Because this thing, which we deduced it must be a lambda, is well typed because the induction hypothesis, so I'll just write it down here. So we're assuming E2 is tau, and E1 is tau 2 arrow tau, E2 is tau 2. So that's how I implied the induction hypothesis. So since this lambda is of type tau 2 arrow tau, it must be that this is the case. So we gotta, I'm just like, what I'm doing is I'm just milking every last bit of information out of the situation I can get in the hopes that I can go forward. All right? So you're with me? Are we okay? Yes? Okay. So this is all the information. I haven't done case 6 yet, but it's going to involve similar things to case 5, so we'll go from there. Okay? All right. So that's all the information we've got now. So what we have to show, right, to show, I want to show that E1, E2 transitions to V for some V. And that V will be of type tau by preservation. Because this was of type tau, that's my E. Because that's the case I'm doing. And I want to show that it terminates, that it has a value. So here's what I do is I take the information I've got. Well, one thing I know, there are many things I know here, but one thing I know is this is the case. This goes to V1 applied to E2. It's also the case that I could transition, no, I can't, no. This is the best I can do right here. Take it back. Everything is fine where I have right here. So we know this, okay? So we know this. Why? Because I said you can simplify, it got erased, you can simplify in E1, and I have a whole sequence of simplifications on E1, and so I run those all down to V1, leaving the applied to E2 in place, okay? So we know that. Which is to say, right, that last thing is lambda x tau 2 dot E prime applied to V1. So now it's clear. So I can go from here to here. This is actually that. So that takes a step to V1 for x E prime. Yes? Oh, I'm sorry. I did something wrong. This should have said E2. I got confused. It didn't look right to me. Okay, I'm sorry. That should have said E2. I don't know what I was thinking. Okay, so that should be that. So that takes a step to E2 for x E prime. Okay? So if we want to eventually get to a value V, then we have to find out somehow that this goes to a V for some V. You see what the problem is? The problem is that I started out with two expressions, E1 applied to E2. And we know that they terminate. So I used the fact that E1 terminates. That's all I care about right here. I used the fact that E1 terminates to get me down to this situation, which is this situation here. Now, the only next step, because you can just verify this, certain amount of things I'm just going to take as for granted. The only thing you can do now, there's no options. The only thing you can do is take this step. This is not a value, it's an application, so you're not done. You take this step, and now you have to reason about a substitution instance of the body of the lambda. That lambda resulted from evaluating E1. In other words, this is an arbitrary piece of code that, okay, it arose from executing E1, but it's not like a piece of E1. You can't dissect E1 and say, aha, in there is V1. No, that's not the case. It is not a piece of E1. Why? Because every time you execute, you substitute and you create new pieces of code. So when you get to a certain situation, like you know that the value is some lambda, you know nothing, as of right now, you know nothing about it. Ooh, this is nasty, okay? This is nasty because, you see, E prime, so I have no, at the moment, I have no information about E prime. And so there's no way for the proof that I'm currently outlining to succeed. That's not going to work. Okay? So what do I need? Okay? What do I need? Well, what I need to know, so if you see where I'm going, I need to strengthen the inductive hypothesis. Okay? So what I'm trying to do now, just in terms of your own proving experience, you try to prove a theorem. If A, then B, by some induction principle. That's the theorem you actually want, no doubt about it. But you go to prove it and you realize merely knowing B about the premises of some induction is not enough to push through the argument. Okay? So you have to strengthen the induction hypothesis. Okay? So here's what I'm going to do. The way in which I'm going to strengthen the induction hypothesis is I'm going to have to state things in such a way that I do get some information about E prime here so that I can use that to keep myself going. All right? So this is what I'm going to do. Now, given my timing, all right, I want to be careful to finish, because Dan is going to take these ideas and then spin them up quite a bit more after the break. So let me make sure I get to this. Okay? All right. So here's what we do. So I'm going to introduce another property. And by the way, notice if it's even possible to say that I only care about termination of things of type nat. Nevertheless, you get into trouble because things of type nat involve things of type blah arrow nat, which themselves involve things of type blah blah arrow nat. Okay? You're not going to get around it by doing anything like this. Okay? This is the essence of higher order computation. The whole idea of functional programming is exactly what I'm going to do next. Okay? So what I do is I introduce a property, a stronger property than termination, called, and this is important, it's called hereditary termination. And I'll write it as ht tau of E. What do I mean by stronger? So what I need is, one, is that I want that ht tau, or let's just do it even for nat, ht nat of E implies T of E, which is termination. So using an adjective, whatever hereditary may mean, I'm going to tell you now, the terminology makes sense because hereditarily terminating implies terminating. That's the way we're doing this. So it's a stronger property. Okay. So I'm going to define things so that this is the case. Okay? And then I'm going to define it in the following way. So what we do is we define this property. So we define ht tau of E by induction on tau. And this is Tate's method. Okay. Gödel's goal was to prove the equivalence of the termination. Tate is the one who actually proved it. Okay, I've forgotten about that. It came to my head. William Tate is he might be retired now, professor at University of Chicago. Okay, and he invented this the idea that I'm doing right now. Okay. So what we do is this. We do it in the following way. I have to define what is ht of nat of E, and I have to define what is ht of tau 1 arrow tau 2 of E. And the idea is going to be this. I'll get back to what I'm going to do here in a minute. The crucial idea is that what I'm doing is I'm associating an invariant with pieces of code, okay, in such a way that, so we do the following thing. E evaluates to a lambda, okay, and for every, you can see how this is going to fit together, for every E1 such that it itself satisfies the invariant of being hereditarily terminating, what we know is that E1 for x, we know that hereditarily terminating E1 for x, E prime. This is the definition here. I'll fill in the other one in a minute, okay? So this is the definition. NB, the type goes down, so to say. That is, I define hereditary termination at function types in terms of hereditary termination at the domain type and at the range type, and then I will define this outright. Okay? You with me? All right. So the condition I'm going to have here is this. either it evaluates to 0 or it evaluates to the successor of E prime with E prime being hereditarily terminating. That's the definition I'm going to use here. What time am I supposed to stop, Zaina?
2 minutes.
Okay, all right, I will do that. Okay, I will be 5 minutes over. Okay, so this is the definition. Now the question is, why is this well defined? That's important. Well, why is it a question? Because I'm defining HT-net in terms of HT-net. Okay? So the answer is, guess what? How should I define the invariant for the natural numbers? Inductively. Okay? I will, but not by induction on natural numbers. That's very important. Okay? So we'll define it as the strongest predicate. I'm not going to, I'll elaborate on this separately. I won't be able to elaborate on it now. It's the strongest predicate satisfying these rules. These principles, whatever that is, the ones that I just wrote right here. Okay? Let's hold that in abeyance because I need to get the higher level architecture down. So this is well defined. What I do is I say HT-net of E is it's the strongest predicate P such that, well, either E evaluates to 0 or E evaluates the successor and P of E prime. Take the strongest such thing. That's a well-defined scenario. Okay? If you're not familiar with inductive definitions of sets or relations or properties, we can have a little tutorial about that. Okay? But you need to know that. That's very fundamental. Okay? It's a curious fact that at universities throughout the world, maybe certainly in the US, there's always an intro to theory of computer science, and they never teach you any useful theory of computer science. Well, okay, it is useful for other things. They never teach you anything like what I'm using here. It's a pity. It's a strange thing. Okay, so don't feel bad if you don't know about it, but I'll just say that. Now here's what we prove. I'll put it over here. Okay, so now there's another hang-up, but we'll get to it in a minute. Okay, so I'm going to have to strengthen the induction hypothesis again. Okay, but the next version of it is theorem V2 says if E is of type tau, then it's hereditarily terminating. And therefore, at nat, it'll be terminating. And then we'll say, and therefore, by strengthening, it's terminating at type tau. Okay. So we get the previous theorem if I can prove this. Okay? All right, do you see this? Well, I don't expect you to see the proof, but I want you to see the logic of my argument. And then the proof is something you work out. Okay? So you see the logic of what I'm doing? Okay. So I'm saying prove something stronger. Now what's cool is on the inductive hypothesis, going back to my broken argument, I don't know just this. Now I know this is hereditarily terminating at tau 2 arrow tau, and I also know it's hereditarily terminating at tau 2. So I get much stronger result now by inductive hypothesis. And look, what does this property mean? It says if E1 evaluates to a lambda, and I take a stat, and then I plug in that, I get something which is hereditarily terminating. Yes, that's exactly what I want. You see, it tells me that hereditarily terminating says if this goes to a value which is a lambda, then because that's hereditarily terminating, this is too. This is exactly right. So, wow, how did that happen? Okay, so what this is this tells us that this guy is hereditarily terminating at the appropriate type. Okay, because of the exact definition right here of hereditarily terminating says if it goes to a lambda and you plug into the body the result something which is hereditarily terminating, which I definitely have, then I get that that's hereditarily terminating. Okay, I rigged this to make the proof go through. Pretty cool. All right. Now, where you pay the piper is you have to show that at natural numbers type, which I'm not going to do here at the board, but it's easy because of the way I've defined it. Okay. All right, so I'm in good shape, it looks like, but there's a worry. It still does, the proof still will not go through. Why? So now we'll say, uh-oh. If we're going by induction on typing, and if I have the typing for a lambda, let's write it like this. So that's my rule. What do I have as a premise? X tau 1, E2 tau 2. In other words, if I have a closed lambda whose type is tau 1 arrow tau 2, the typing rule can be inverted, and we know that we have that as a premise. The theorem is only stated about closed terms, but I need to get information about an open term. You see? No induction. Like if you think of doing the proof by induction, there's no inductive hypothesis because the theorem only applies to closed terms. It's not applicable to this. So I have to strengthen the theorem again. Okay? So here's what we do. So that doesn't work. So I have to account for open terms. But you must account for open terms. You can't just confine your attention to closed terms. So we get to theorem 3, version 3. Theorem V3, Tate. If gamma tells me this, and now let me write a little convenient abbreviation. HT capital gamma of little gamma, I'll say what that is in a minute, then HT tau of gamma hat of E. What does this mean? This means suppose that capital gamma is x1 tau 1 through xn tau n, then little gamma says send x1 to E1, send xn to En. It's a substitution. It says replace x1 by E1, replace xn by En, such that each one of these is hereditarily terminating at the correct type. So we know that ht of tau 1 of E1 up to ht of tau n of En. That's what I mean. That's what this is packaged up to mean that. And this just means do the substitution. Plug it in. So if it happens that gamma is empty, then there are no substitutions because there are no variables, and we get the previous theorem. And if we get the previous theorem, we get the previous theorem, which is the one we wanted. Okay? And then we're done. So this is Tate's method. 2 stages of strengthening the inductive hypothesis. Okay? So one is introducing the idea of hereditary termination, and second of all, strengthening the theorem to consider open terms. Boom. Now you're done. And in categorical jargon, I prove something about the mappings in order to prove something about the elements. Ed will tell you about how you think about elements in category theory in terms of mappings, and he will explain that. Okay? So that's just an allusion to what Ed is going to do. Generally speaking, except in certain situations of well-pointed categories, they're called, you cannot consider only the elements, you have to consider the mappings, okay, approximately, okay? So that will come up, okay? So the ideas, I want you to see eventually how all the various ideas fit together, and that we are, as Freud said, practicing the science of the non-arbitrary, okay? And so I will continue with that later. Okay, so that's enough for now. I don't have time to go through all the steps of the proof. It's in the book. Okay, great thing about having written a book. Okay, so it's in the book. Okay, so thanks for your attention, and Dan will resume in a little bit after the break.